Hello there, and welcome to the Dozing Explorer. I am so glad you have found this space tonight, a haven designed for rest and contemplation. As you settle in, let go of the day's concerns.
There is nothing you need to achieve here, no problems to solve. Your sole focus is allowing yourself to unwind. Find a comfortable position, close your eyes if you feel inclined, and let my voice be an anchor as your thoughts begin to drift. Tonight, we embark on a journey through the perplexing and fascinating landscape of time. We won't be tackling rigorous physics problems, but rather meandering through the strange loops, baffling questions, and subtle paradoxes that arise when we contemplate time's true nature. We will drift through ideas of relativity, where time stretches and compresses, and ponder the very direction of its flow. This is an exploration into one of the universe's most fundamental and intimate mysteries, a concept that governs our lives yet constantly eludes our full grasp. We will contemplate time not just as the ticking of a clock, but as a dimension interwoven with space, a current carrying us from a remembered past towards an unknown future. We'll explore the curious ways our own minds perceive its passage, how moments can feel like eternities and years can vanish in a breath. This journey touches upon the profound uncertainty that lies at the heart of existence, where the steady stream we experience might dissolve into something far stranger under closer inspection. It is a voyage into the very fabric of reality. And just before we begin this exploration, if you find these thoughtful wanderings help you relax and find stillness, perhaps consider liking and subscribing. It's a simple gesture that assists others searching for rest in discovering this channel, and it allows these explorations to continue reaching those who need them. But for this moment, let those thoughts recede.
Nothing is required of you now.
Your only task is relaxation. Breathe deeply, feel the support beneath you, and grant yourself permission to let go. Your mind is free to follow these ideas, to wander among them, or to drift off entirely into sleep whenever it feels ready. Let the current carry you. Time does not flow at the same rate for everyone. Our everyday experience suggests a universal clock, ticking away the moments identically for all observers. Yet, the physics unveiled over the last century paints a different picture. Albert Einstein's theory of relativity revealed that the passage of time is not absolute but relative, intricately linked to an observer's motion and the gravitational field they inhabit. An astronaut traveling at high speed experiences time passing more slowly than someone stationary on Earth. Similarly, someone living at sea level experiences time moving infinitesimally slower than someone atop a high mountain. Due to the difference in gravitational pull, the steady, unwavering tick-tock we imagine is not a fundamental feature of the cosmos, but rather a local approximation. The universe contains countless clocks, each keeping its own distinct rhythm. Existence unfolds at varying tempos across the cosmos. Your brain constructs your experience of time's passage. The subjective feeling of time moving fast or slow, smooth or fragmented is not a direct perception of an external reality, but an intricate creation of our own minds. Our brains gather information from our senses, integrate it with memory and expectation, and weave it into a coherent narrative that includes a sense of duration and progression. Factors like attention, emotion, and even body temperature can significantly alter this internal construction. When deeply engrossed, hours might vanish unnoticed. During periods of boredom or anxiety, minutes can stretch into seeming eternities. The clock on the wall may be steady, but the clock within our consciousness is remarkably fluid and personal. Your mind is the ultimate arbiter of the moments you inhabit. The feeling of a smooth, continuous now might be an illusion. We typically experience consciousness as an unbroken stream, a flowing river of the present moment. However, neuroscience suggests this perceived continuity might be a clever trick performed by the brain. Our sensory systems process information at different speeds. Sight is faster than sound, which is faster than touch. The brain must collect these staggered inputs, process them, and then retrospectively bundle them together to create the impression of a single, unified now. What feels like the present is likely a constantly updated reconstruction of the very recent past, smoothed over by our neural architecture. The seamless river of awareness may actually be composed of countless discrete, integrated snapshots. The present moment is perhaps a masterpiece edited by the mind. Time can seem to stretch when you are afraid or excited. Many people report experiencing moments of crisis, a car accident, a sudden fall, as if they happened in slow motion. This isn't because external time actually slows down, but likely because the brain kicks into overdrive during high alert situations. The amygdala, involved in processing fear, becomes highly active and instructs other brain regions to record memories with much greater density and detail than usual. When you later recall this densely packed memory, it feels longer than it objectively was. It's not that time stretched, but that your internal recorder captured far more frames per second, making the playback feel extended. In moments of intensity, the mind expands the chronicle of the instant. It can feel compressed when you are engaged or having fun. Conversely, when you are deeply absorbed in an enjoyable activity, reading a captivating book, immersed in creative work, or spending time with loved ones, hours can seem to melt away in what feels like minutes. This common experience, often summarized as "time flies when you're having fun," likely relates to attention. When fully engaged, your brain dedicates fewer resources to monitoring the passage of time itself. Without this active self-monitoring, our internal clock seems to run faster, and large intervals pass by almost unnoticed until we re-engage with external cues. Absorption dissolves the awareness of duration. There is no universal now across the cosmos. Einstein's special relativity revealed a profound truth. Simultaneity is relative. Two events that happen at the exact same moment for one observer might happen at different moments for another observer moving relative to the first. This means there is no single, objective, present moment that encompasses the entire universe. Your now is personal, defined by your position and motion within the four-dimensional fabric of space-time. An observer on a distant galaxy has their own distinct now, and there is no physically preferred way to align them. The universe exists not as a single unfolding moment, but as a vast collection of relative perspectives. The present is a local phenomenon, not a cosmic decree. What you perceive as now depends on where you are and how you are moving. Imagine trying to synchronize clocks with someone on Mars. Light signals take minutes to travel between the planets. By the time you receive a signal indicating their now, that moment has already passed for them. Because information cannot travel faster than light, defining a shared present moment across distances becomes impossible. Furthermore, as relativity shows, observers in relative motion will disagree on which distant events are happening now. Your perception of the present is inextricably tied to your unique coordinates in space-time, but each observer occupies their own distinct temporal viewpoint. The shortest possible unit of time is called Planck time. According to our current understanding of physics, particularly quantum mechanics and general relativity, there might be a fundamental limit to how finely we can divide time. Below a certain incredibly small interval, known as the Planck time, approximately 1043 seconds, the familiar concepts of time and space may break down into a quantum foam, where causality and sequence lose their meaning. It represents the theoretical resolution limit of the universe's clock, the smallest tick that makes physical sense in our current theories. Time itself might have a granular structure at its most fundamental level. Existence may unfold not as a smooth flow, but in indivisible, infinitesimal steps. Why does time seem to move only forwards? This is one of the deepest mysteries in physics. While we can move freely back and forth in the three dimensions of space, our experience of time is relentlessly unidirectional. We remember the past, we experience the present, and we anticipate the future, but we never seem to move in reverse. Broken glasses don't reassemble.
Spilled milk doesn't flow back into the carton.
This perceived one-way flow is often called the arrow of time. Identifying the physical origin of this asymmetry remains a profound challenge. The current of time carries us only downstream. The arrow of time might be linked to the universe's increasing disorder. The most widely accepted explanation for time's directionality points to the second law of thermodynamics. This law states that the total entropy or disorder of a closed system tends to increase over time. Processes naturally move from states of order to states of disorder. A whole egg, ordered, becomes a scrambled egg, disordered. The universe itself began in a remarkably ordered low-entropy state at the Big Bang and has been becoming more disordered ever since. Perhaps our perception of time flowing forwards is simply our observation of this fundamental tendency towards increasing cosmic messiness. We perceive time's flight as the universe slowly unwinds. Your feet are technically aging slower than your head. Because your feet are slightly closer to the center of the Earth than your head, they are in a slightly stronger gravitational field. According to general relativity, this means time is passing infinitesimally slower for your feet than for your head. The difference is absurdly small, on the order of femtoseconds over a lifetime, but it is a real physical effect. Even your own body experiences a minuscule temporal gradient. Height grants a fleeting, imperceptible advance in age. GPS satellites must constantly adjust their clocks to account for time dilation. The global positioning system relies on incredibly precise timing signals transmitted from satellites in orbit. These satellites experience both velocity-based time dilation, running slower than Earth clocks, and gravity-based time dilation, running faster due to being in a weaker field. The gravitational effect is larger, so their clocks actually run slightly faster than ground clocks. If these relativistic effects were not precisely accounted for, the entire GPS system would fail within minutes, leading to navigation errors miles off course. Precise navigation depends on acknowledging time's subtle elasticity. Space and time are interwoven into a single fabric called space-time. Before Einstein, space and time were considered separate and absolute backdrops against which events unfolded. Relativity revealed that they are intrinsically linked, forming a unified four-dimensional continuum. What one observer perceives as purely spatial distance, another observer in motion might perceive as a mixture of spatial and temporal separation. They are different dimensions of a single, deeper reality. The stage upon which the universe performs is a unified entity. Massive objects create curves or dimples in this space-time fabric. General relativity describes gravity not as a force pulling objects together, but as a consequence of mass and energy warping the geometry of space-time. Imagine a heavy ball placed on a stretched rubber sheet. It creates a dip. Similarly, planets, stars, and galaxies create curvatures in the four-dimensional space-time around them. Objects moving nearby simply follow the straightest possible paths through this curved geometry. Matter tells space-time how to curve. Gravity is the feeling of moving through this curved space-time. When you throw a ball, it follows a curved path, not because a force is pulling it down, but because it is following a geodesic, the straightest possible line, through the space-time curved by the Earth's mass. What we perceive as the force of gravity is actually just the manifestation of this underlying space-time geometry. We are constantly navigating the subtle slopes and valleys in the fabric of reality. Space-time tells matter how to move. Your motion through space affects your motion through time. A profound consequence of the unification of space and time is that all objects are constantly moving through space-time at a fixed rate, the speed of light. If you are stationary in space, all of this motion is directed through the time dimension. As you begin to move through space, some of that motion is diverted from the time dimension into the spatial dimensions. This redirection is why moving clocks run slow, They are simply traveling less rapidly through time to compensate for their velocity through space. Speed through space is borrowed from speed through time. The faster you move through space, the slower you move through time. This trade-off becomes extreme as you approach the speed of light. An object traveling at light speed, like a photon, directs all its space-time motion through the spatial dimensions, leaving none for the time dimension. Consequently, it experiences no passage of time. For anything with mass, reaching the speed of light is impossible, but approaching it results in progressively slower temporal passage relative to a stationary observer. The cosmic speed limit enforces a fundamental exchange rate between distance and duration. The speed of light is the ultimate cosmic speed limit. Special relativity dictates that nothing with mass can ever reach the speed of light, and nothing, mass or energy, can exceed it. This speed, approximately 300,000 kilometers per second in a vacuum, is not just the speed of light. It is the fundamental speed of causality in the universe. It represents the maximum rate at which information or influence can travel through space-time. It is the universe's absolute velocity ceiling. Objects moving near light speed also appear shorter in the direction of motion. Another counterintuitive consequence of special relativity is length contraction. From the perspective of a stationary observer, an object moving at relativistic speeds will appear compressed along its direction of travel. Its length in that dimension shrinks, becoming progressively shorter as its speed increases. This effect, like time dilation, is necessary to ensure the speed of light remains constant for all observers. Speed compresses distance along the line of travel. Two events that seem simultaneous to one observer may not be simultaneous to another. Imagine two lightning strikes hitting the front and back of a moving train. An observer standing on the ground midway between the strikes might see them happen at the same time. However, an observer sitting in the middle of the train, moving towards the front strike and away from the back strike, would see the front strike happen first. Relativity shows there is no absolute same time for events separated in space. It depends on the observer's motion. Simultaneity lies in the eye of the beholder. A black hole is a region where space-time is curved infinitely steeply. When a massive star collapses under its own gravity, if it is massive enough, it can crush itself down to a point of zero volume and infinite density, a singularity. This singularity warps the space-time around it so extremely that it creates a boundary, the event horizon, from which nothing, not even light, can escape. It represents gravity taken to its ultimate extreme. It is a place where the fabric of reality descends into an abyss. Time effectively stops at the event horizon of a black hole for an outside observer. Due to extreme gravitational time dilation, someone watching an object fall towards a black hole would see its clock tick progressively slower. As it reached the event horizon, its clock would appear to stop completely. The object would seem frozen in time at the boundary, its light becoming infinitely redshifted and fading from view. From the outside, the final moment of infall lasts forever. The edge of a black hole is a horizon where time appears to cease. Inside a black hole, space and time might swap roles. According to the mathematics of general relativity, the nature of space-time coordinates changes dramatically inside the event horizon. The radial direction, moving towards the singularity, takes on the character of time. It becomes inevitable, always moving in one direction. The dimension we previously knew as time might become more space-like, potentially allowing movement within it, though escape is still impossible. It's a theoretical realm where the fundamental coordinates of reality are transformed. The inward path becomes the only possible future. Could you go back in time and accidentally prevent your own birth? This thought experiment, known as the grandfather paradox, highlights the potential logical contradictions inherent in the idea of traveling to the past. If you could change the past in a way that eliminates the conditions necessary for your own existence or your motivation to time travel in the first place, you create an impossible causal loop. It raises the question of whether the past is immutable or if paradoxes simply cannot physically occur. Can the stream of history be dammed by its own future? Some solutions suggest parallel universes are created to avoid paradox. One speculative way to resolve the grandfather paradox is the many worlds interpretation, borrowed from quantum mechanics. In this view, any action that could create a paradox instead causes the timeline to split, creating a new parallel universe where the altered history plays out. The time traveler doesn't change their own past, but shifts into a different history altogether.
Leaving their original timeline untouched, every choice echoes into a separate,
unfolding reality. Or perhaps the laws of physics simply prevent paradoxical actions. Another possibility is that the universe has built-in self-consistency mechanisms. Perhaps any attempt to create a paradox would inevitably fail in some unforeseen way. The gun might jam, you might have a change of heart, or some other event might intervene to ensure that the timeline remains logically consistent. The laws of causality might be inherently self-protecting. History might possess an inherent inertia, resisting alteration. What if you gave Shakespeare a copy of Hamlet written in the future? This scenario illustrates the bootstrap paradox, also known as an ontological paradox or causal loop. If Shakespeare simply copies the play you gave him, which he then writes, which is then preserved for you to take back to him, where did the actual information, the creative spark for Hamlet, originate? It seems to exist without ever having been created, trapped in a self-contained loop across time. Information becomes a traveler with no point of origin. Memory plays a crucial role in our sense of time passing. Our ability to form and recall memories is fundamental to our experience of duration and sequence. Without memory, each moment would feel disconnected, and the concept of past would lose its meaning. It is the accumulation of memories, the continuous recording of experiences that allows us to construct a personal timeline and perceive ourselves as moving through a progression of events. The feeling of time's passage is deeply intertwined with the act of remembering what came before. Time's arrow is feathered with the recollections of moments gone by. Every memory you recall is subtly altered in the present. Remembering is not like replaying a video recording. It is an active process of reconstruction. Each time you access a memory, your brain rebuilds it, and this process can incorporate new information, current emotions, and subsequent experiences. This means that memories are not static archives, but are dynamic and malleable, often changing slightly with each recall. The past, as we remember it, is constantly being subtly reshaped by the present. Recollection is not just retrieval, it is a form of recreation. Time might not be a fundamental property of the universe, but an emergent one. Some physicists exploring theories of quantum gravity speculate that time, as we perceive it, is not a basic ingredient of reality. Instead, it might be an emergent phenomenon, something that arises from a deeper, timeless level of existence, much like the sensation of temperature emerges from the collective motion of countless individual atoms. In these speculative frameworks, the universe at its most fundamental level might be static, and the flow of time we experience could be a kind of illusion or a feature only of macroscopic systems. The river of time might spring from a deeper, motionless ocean. Some physicists believe time itself might arise from quantum entanglement. One intriguing idea linking time to quantum mechanics suggests that the flow of time could be related to the phenomenon of entanglement, the deep connection between quantum particles. In this view, the universe as a whole exists in a static quantum state, but observers within the universe, who are entangled with parts of it like clocks, perceive the state of the systems they are measuring as changing relative to their own state. This perceived change, driven by the evolving pattern of entanglement, is what we experience as the passage of time. Time could be the name we give to the changing relationship between entangled parts of reality. The concept of time doesn't exist within some fundamental physics equations. A key equation in attempts to unify gravity and quantum mechanics, the Wheeler-DeWitt equation, describes the wave function of the entire universe. Intriguingly, this equation contains no variable explicitly representing time. This mathematical curiosity has led some physicists to propose that time truly vanishes at the most fundamental quantum level of the cosmos. The universe, in this view, simply is a timeless entity, and the flow we perceive is secondary. At the deepest level, perhaps nothing ever truly happens. Your internal body clock doesn't perfectly match the 24-hour day. Most living organisms possess internal biological clocks known as circadian rhythms that regulate cycles of sleep, wakefulness, hormone release, and metabolism. In humans, this internal clock, located in a part of the brain called the suprachiasmatic nucleus, naturally runs on a cycle slightly longer than 24 hours. We rely on external cues, primarily the daily cycle of sunlight, to reset this internal clock each day and keep it synchronized with the Earth's rotation. Without sunlight, our internal sense of a day would slowly drift. Our bodies keep their own intrinsic time, slightly out of step with the world. Light itself experiences no time passing at all. According to special relativity, time dilation becomes infinite for an object traveling at the speed of light. This means that from the perspective of a photon, a particle of light, its entire journey happens instantaneously. The moment it is emitted and the moment it is absorbed are, for the photon, the exact same moment in time, even if billions of years have passed for outside observers during its voyage across the cosmos. For light, the beginning and the end of the journey are one. For a photon traveling across the universe, the journey is instantaneous. Imagine a photon emitted from one of the first stars, traveling for over 13 billion years before being captured by the James Webb Space Telescope. From our perspective, its journey was immensely long, but from the photon's own frame of reference, no time elapsed. It experienced its creation and its absorption simultaneously. The vastness of cosmic time simply does not exist for light itself. Light traverses eternity in a timeless instant. Does time have a beginning and an end? This is a fundamental cosmological question. Our current understanding suggests that the Big Bang marks the beginning of time as we know it, the start of the universe's expansion and evolution. Whether time will have an end depends on the ultimate fate of the universe. Will it expand forever, leading to a cold, dark heat death? Will it recollapse in a big crunch? Or will it be torn apart by accelerating expansion in a big rip? The destiny of time is tied to the destiny of the cosmos itself. The ultimate clock may run down, stop, or be shattered. The Big Bang might represent the beginning of time as we know it. According to the standard cosmological model, the universe began in an incredibly hot, dense state about 13.8 billion years ago and has been expanding ever since. Asking what happened before the Big Bang might be a meaningless question, akin to asking what is north of the North Pole. If time itself began with the Big Bang, then there simply was no before. It marks the origin point of the temporal dimension itself within our current understanding. It may be the moment that the cosmic clock first started ticking. Traveling near the speed of light makes time slow down for the traveler. One of the most famous predictions of Einstein's special relativity is time dilation due to velocity. The faster an object moves through space relative to an observer, the slower that object's time appears to pass from the observer's perspective. For everyday speeds, this effect is minuscule, but as you approach the speed of light, it becomes dramatic. A hypothetical astronaut traveling at 99% the speed of light would experience time passing about 7 times slower than someone on Earth. Speed is a current that slows the river of time. astronauts in orbit age slightly slower than people on Earth. This is a real and measurable effect of both special and general relativity. Astronauts on the International Space Station are moving very fast, special relativity effect slowing their time, but are also in a slightly weaker gravitational field, general relativity effect, speeding their time up relative to the surface. The velocity effect is stronger, resulting in them aging a tiny fraction of a second less than people on the ground over the course of a mission. It's a subtle, real-world confirmation of time's malleability. Orbiting the Earth offers a minuscule sip from the fountain of youth. This effect is called time dilation. It applies not just to clocks, but to all physical processes, including biological aging. From the perspective of a stationary observer, all events occurring within a fast-moving reference frame appear to unfold more slowly. It is a fundamental consequence of the constancy of the speed of light for all observers and the intertwining of space and time. Time stretches and thins for those on a swift journey. Gravity also warps the flow of time. Einstein's general relativity revealed another form of time dilation, this one caused by gravity. Time passes more slowly in stronger gravitational fields. The closer you are to the center of a massive object, the slower your clock ticks relative to someone farther away. This is because gravity is understood as a curvature of space-time, and this curvature affects the temporal dimension as well as the spatial ones. Mass exerts a subtle drag on the progression of moments. Time passes more slowly closer to a massive object, like a planet or a star. A clock placed on the surface of the Sun would run measurably slower than a clock on Earth. Similarly, a clock on Earth runs slightly slower than a clock in deep space, far from any significant gravitational influence. The difference is tiny in weak fields like Earth's, but becomes extreme near objects like neutron stars or black holes. Gravity creates gradients in the flow of time itself. The universe's great masses create pools where time lingers. Where did the information originally come from in a causal loop? The bootstrap paradox challenges our fundamental understanding of cause and effect and the origin of information. In such a loop, the information, like the text of Hamlet, seems to have no beginning, simply existing eternally within the circular timeline. It implies that information might not always need a distinct point of creation, potentially violating our intuitions about how things come to be. The effect becomes its own cause, in an endless, cyclical dance, the predestination. Paradox suggests you cannot change the past,
Only fulfill it.
This paradox proposes that any attempt to travel back in time and alter events is doomed to fail because your actions were already part of the history that led to the future you came from. You might inadvertently cause the very event you were trying to prevent, or your presence might simply be another detail in the already written story of the past. Free will clashes with a potentially immutable history. Your journey into the past was perhaps always part of its fabric. Your attempt to change the past might be the very event that caused it to happen. Imagine traveling back to prevent a tragic fire, only to accidentally knock over the lantern that starts it. In this scenario, your intervention doesn't alter history, but instead becomes the necessary catalyst for the events you already knew. The timeline accommodates your presence, weaving your actions into the existing sequence of cause and effect, ensuring consistency. The effort to rewrite history becomes the ink that writes it. Wormholes are theoretical tunnels through space-time that might allow time travel. General relativity permits mathematical solutions that describe shortcuts through space-time. Connecting distant points like a tunnel connects two valleys. These hypothetical structures are called wormholes or Einstein-Rosen bridges. If the two mouths of a wormhole were manipulated correctly, perhaps by moving one at relativistic speeds or placing it in a strong gravitational field, it could potentially connect not just different locations, but different moments in time. Space-time might contain hidden passages between moments. A wormhole might connect two different points in time. If one end of a wormhole undergoes significant time dilation relative to the other, entering one mouth and exiting the other could result in arriving at an earlier or later time. This provides a theoretical mechanism for time travel. Although it relies on the existence and stability of these exotic structures, a shortcut through space could become a detour through duration. Creating or stabilizing a wormhole would require exotic forms of matter or energy. While mathematically possible, traversable wormholes appear physically problematic. Keeping the throat of the wormhole open against its tendency to collapse would require material with negative mass or negative energy density properties, not known to exist in the real universe in sufficient quantities. Building a stable time tunnel seems beyond our current
Understanding of physics, the
pathways through time may require keys made of impossible materials. Some theories propose closed time-like curves, paths through space-time that loop back on themselves. Certain solutions in general relativity, particularly those involving rotating masses or exotic geometries, allow for the existence of paths through space-time that return to their starting point, not just in space, but also in time. An object traveling along such a closed time-like curve, CTC, would experience its own history, repeating in an endless loop. Existence could become a journey on a circular track. Traveling along such a curve would mean returning to your own past. Following a CTC would inherently involve time travel into one's own past, bringing with it all the potential paradoxes associated with altering history. The existence of CTCs in a physical theory is often seen as problematic, suggesting either that such geometries do not occur in reality or that some physical principle like quantum effects or self-consistency prevents paradoxes from
rising. The universe might contain paths that lead
inevitably back to yesterday. Rotating cylinders of infinite length might create closed time-like curves. A theoretical construct proposed by physicist Frank Tipler suggests that an immensely dense cylinder, infinitely long and spinning rapidly on its axis, could warp space-time in such a way as to create paths that loop back in time. Objects following specific spiral trajectories around such a cylinder could potentially return to their own past. However, the requirement of infinite length and the potential instabilities make the Tipler cylinder a highly speculative and physically implausible concept, more of a thought experiment exploring the limits of general relativity than a practical blueprint for a time machine. Vast, spinning cosmic structures could theoretically twist the pathways of duration. Is the future fixed, or is it open to change? This question lies at the heart of debates about free will and determinism, and it becomes particularly relevant when considering time travel. If the future is already written, a concept sometimes associated with the block universe idea, where all time exists simultaneously, then traveling to the past might be possible, but changing it would be impossible, as your actions would already be part of that fixed history. Conversely, if the future is open and probabilistic, then altering the past could have cascading, unpredictable consequences, potentially making such travel inherently paradoxical or prohibited. Does the river of time flow towards an ocean already mapped, or into an expanse of open possibility? Time travel to the past is possible. Why haven't we met any time travelers? This question forms the crux of the Fermi paradox as applied to time travel. If future civilizations develop the technology to visit earlier eras, one might expect some evidence of their presence, artifacts, documented encounters, or even just subtle historical anomalies. The apparent absence of such visitors could imply that backward time travel is impossible, extremely difficult, carefully regulated, or perhaps the travelers are strictly observing a non-interference directive. Or maybe the changes they make create alternate timelines we cannot perceive. The silence from the future echoes loudly in the halls of the present. Perhaps travel is only possible to the future, not the past. While backward time travel is fraught with potential paradoxes, forward time travel is a well-established consequence of relativity. Traveling at high speeds or spending time in strong gravitational fields demonstrably slows the passage of time for the traveler relative to the outside world, effectively allowing them to journey into the future at an accelerated rate. This one-way aspect of temporal displacement seems more consistent with our observed universe and avoids the logical contradictions associated with altering history. The current may allow leaps downstream, but forbid voyages against the flow. We remember the past, but we do not remember the future. This fundamental asymmetry in our conscious experience is deeply intertwined with the arrow of time. Our minds seem built to record events that have occurred, forming memories, while the future remains a realm of anticipation and uncertainty. This psychological arrow of time, the feeling of progressing from a known past to an unknown future, aligns perfectly with the thermodynamic arrow, increasing entropy, suggesting a deep connection between physical processes and our subjective experience of time's direction. Our consciousness seems oriented only towards the wake, not the bow. Why does time have this built-in directionality? While the second law of thermodynamics offers a compelling explanation based on entropy, it doesn't fully answer why the universe started in such a highly ordered, low-entropy state in the first place, providing the initial condition necessary for entropy to increase. The ultimate origin of time's arrow remains a subject of ongoing investigation, potentially linked to the specific conditions of the Big Bang or even deeper, underlying asymmetries in the laws of physics yet to be discovered. The source of time's unidirectional current remains a profound cosmological riddle. Entropy, the measure of disorder in a system, always seems to increase over time. From a neatly arranged room becoming messy, to ice melting in warm water, to stars burning out and dispersing their energy, the universe exhibits a pervasive tendency towards greater randomness and disorganization. The second law of thermodynamics formalizes this observation, stating that the total entropy of an isolated system can only stay the same or increase, never decrease. This relentless march towards disorder appears to be the most robust physical marker defining the forward direction of time. The universe constantly moves towards a state of greater diffusion and equilibrium. An egg can scramble, but a scrambled egg cannot spontaneously unscramble. This simple, everyday example perfectly illustrates the principle of increasing entropy and the arrow of time. The number of ways the molecules in an egg can be arranged in a scrambled state is vastly greater than the number of ways they can be arranged in the highly ordered state of a whole egg. Natural processes tend to move towards the states with the highest probability, which are almost always the more disordered ones. Reversing this process spontaneously is statistically impossible. Time crystals are structures that repeat patterns in time, not just space. Normal crystals have atoms arranged in a repeating pattern in space. Time crystals, first proposed theoretically and now created in laboratories, are quantum systems whose lowest energy state exhibits periodic motion. They spontaneously break time translation symmetry, meaning they behave differently at different moments in time, even without any energy input. They are like perpetual motion machines operating at the quantum level, ticking indefinitely. Matter can possess an intrinsic rhythm, a clock woven into its very ground state. Can information truly be destroyed, or is it conserved throughout time? A fundamental principle in physics, particularly in quantum mechanics, is unitarity, which implies that information is never truly lost. You can burn a book, but the information it contained is still encoded, albeit scrambled, in the configuration of smoke, ash, and heat. This principle leads to profound paradoxes when considering processes like black hole evaporation. Does the universe keep meticulous records, never truly erasing anything? The black hole information paradox questions what happens to information that crosses an event horizon. According to classical general relativity, anything falling into a black hole is lost forever. However, Stephen Hawking showed that black holes eventually evaporate via Hawking radiation. If this radiation is purely thermal and random, then the information about what fell in seems to be destroyed, violating quantum principles. This conflict between gravity and quantum mechanics remains unresolved. Do black holes act as cosmic archives or ultimate shredders? Hawking radiation might allow information to slowly leak back out over eons. One proposed resolution to the information paradox suggests that the outgoing Hawking radiation is not perfectly random, but contains subtle correlations that encode the information about the matter that formed the black hole. This information would emerge incredibly slowly and in a highly scrambled form over the black hole's multi-trillion-year evaporation process, preserving unitarity but in a way that is practically impossible to decode. Information might escape its prison, but disguised beyond recognition. Does only the present moment exist, presentism? This philosophical view holds that only the things that exist now are real. The past existed but no longer does, and the future does not yet exist. Under presentism, the flow of time is a fundamental aspect of reality, bringing moments into existence and then consigning them to non-existence. It aligns well with our intuitive experience of a moving present. Is reality confined solely to the thin, advancing edge of becoming? Or do past, present, and future all exist simultaneously, eternalism? This alternative view, often called the block universe theory, is more compatible with relativity. It suggests that all moments in time, past, present, and future, are equally real and exist concurrently within the four-dimensional space-time block. The passage of time is seen as a subjective illusion, like following a single frame of a movie reel that contains the entire film from beginning to end. Is the whole cosmic story already written, spanning across a static landscape of time? Under eternalism, the flow of time is just our subjective perception. If all moments exist equally, then the feeling that time is flowing or moving is purely a feature of our consciousness, perhaps related to the way we process information sequentially or form memories. Our awareness travels along the time dimension of the block universe, creating the illusion of passage, but the block itself remains static and unchanging. Our consciousness might be a cursor moving across a fixed text. Why does time seem to pass faster as we get older? This common subjective experience is a well-known psychological phenomenon. Several theories attempt to explain it. One suggests that our perception of time is relative to our total lifespan. Each passing year represents a smaller fraction of our accumulated experience, making it feel shorter. Another points to the decreasing frequency of novel experiences as we age. Routine makes time seem to blend together and pass more quickly. Duration seems to shrink as the archive of our days grows larger. Perhaps it's related to how many new memories we are forming. Childhood and youth are typically filled with novel experiences, learning, and significant life events, leading to the formation of many distinct memories. As life becomes more routine in adulthood, fewer unique memories are laid down per unit of time. When we look back, periods rich in memories feel longer, while periods of routine seem compressed, potentially contributing to the feeling of time accelerating. The density of recollection shapes our perception of past intervals. How do different cultures perceive and measure time? While the physical passage of time is universal, its cultural conception varies widely. Some cultures have a strongly linear view, emphasizing progress and deadlines. Others have a more cyclical understanding, tied to seasons, rituals, or recurring astronomical events. Concepts like punctuality, the value placed on speed versus patience, and even the way time is linguistically structured differ significantly across the globe. Time wears different cultural garments around the world. Some cultures have a more cyclical view of time rather than linear. Many indigenous and ancient cultures perceive time less as an arrow moving forward and more as a repeating cycle, like the turning of seasons, the phases of the moon, or the patterns of birth, life, and death. This cyclical perspective often fosters a different relationship with the past as ever-present and the future as a return rather than a completely new frontier. History can be seen not just as a line, but as a recurring spiral. Our language shapes how we think about time, e.g., time is money, wasting time. The metaphors we use to talk about time reveal our underlying cultural assumptions. In many Western cultures, time is conceptualized as a valuable commodity that can be spent, saved, wasted, or invested. This linguistic framing influences our behavior and priorities, often leading to a focus on efficiency and scheduling. Other languages might use different metaphors, reflecting alternative ways of relating to duration. The words we use for time become the containers for our experience of it. Is now a sharp point or a fuzzy duration? Philosophically and psychologically, the nature of the present moment is elusive. Is it an infinitely thin boundary between past and future, or does it possess a certain thickness and experiential duration? Our conscious awareness seems to integrate information over short timescales, suggesting that the subjective now might be a brief window rather than an instantaneous point. The present moment might have a brief but noticeable temporal thickness. How long does the present moment last? Psychological studies attempting to measure the duration of the subjective present often arrive at figures around 2 to 3 seconds. This seems to be the time scale over which our brain integrates sensory information into a coherent conscious experience, the window within which events feel simultaneous or part of the immediate now. Anything longer starts to feel like a sequence extending into the past. Our conscious awareness seems to inhabit a brief, sliding window of reality. Can we truly experience the present, or are we always perceiving the immediate past? Given that neural processing takes time, the conscious experience we label as now is inevitably a reconstruction based on sensory information that arrived milliseconds or even hundreds of milliseconds earlier. Light must travel from an object to our eyes, signals must travel up the optic nerve, and the brain must process this information. By the time we become aware of an event, it has already technically happened. Consciousness might be perpetually chasing the receding tail of reality. Our brain synchronizes these signals to create a coherent, present, different. Senses transmit information to the brain at different speeds. The brain performs a remarkable feat of temporal calibration, subtly adjusting the timing of these signals so that we perceive events in a unified way. A simultaneous sound and sight are typically experienced as simultaneous, even though the raw signals arrived at different times. This active synchronization creates the smooth, coherent present we inhabit. The mind acts as a conductor, bringing different sensory inputs into temporal harmony. Déjà vu might be a glitch in this temporal processing. The unsettling feeling of having experienced a new moment before could arise from a brief delay or miscommunication between different brain pathways involved in perception and memory formation. One pathway might register the experience fractionally before another, leading the later signal to be mistakenly interpreted as a memory rather than a fresh perception, creating a false sense of familiarity for an objectively new event. It could be an echo in the mind's temporal processing chambers.
Order dissolves easily into chaos.
Chaos rarely coalesces back into order. This increase in entropy might define the arrow of time. Many physicists believe that the thermodynamic arrow of time is the fundamental arrow of time. Our perception of time flowing forwards could simply be our observation of this universal trend towards increasing disorder. We experience cause-preceding effect because processes that increase entropy happen naturally in one direction, creating the sequence we perceive as temporal progression. Time's direction could be the unfolding of probability. The universe began in a very low entropy, highly ordered state. For entropy to increase, the universe must have started in a condition of incredibly low entropy. The smooth, uniform state shortly after the Big Bang represents a profound level of order compared to the potential for disorder. Explaining this highly improbable initial condition is one of the major challenges in cosmology,
as it is the necessary starting point for the
thermodynamic arrow of time to emerge. The cosmic story began with an extraordinary degree of neatness. Its journey towards maximum entropy might be what we perceive as time's flow. If the universe started highly ordered and is inevitably moving towards a state of maximum disorder, a uniform, lukewarm heat death, then our experience of time passing could be fundamentally linked to being part of this cosmic scale process. We are carried along on the current of increasing entropy, perceiving the stages of this unfolding process as the past, present, and future. Our perception of time could be the universe relaxing towards its final state. But why was the early universe so ordered to begin with? This remains a deep cosmological puzzle known as the past hypothesis. Why did the Big Bang produce a state of such low entropy?
Was it a random fluctuation?
Does it require new physics beyond the standard model, such as cosmic inflation? Understanding the origin of this initial order is crucial for fully understanding the origin of time's arrow itself. The beginning holds the key to the direction of everything that follows. Some processes at the quantum level might
Not obey this strict forward arrow.
While macroscopic processes are dominated by increasing entropy, the fundamental laws governing individual particle interactions are often time-symmetric, meaning they work equally well forwards or backwards. Certain subtle interactions involving the weak nuclear force do exhibit a slight time asymmetry, CP violation, but it's unclear if this microscopic arrow is sufficient. To explain the macroscopic arrow of time we experience, the smallest constituents of reality may not share our sense of temporal direction. Is the psychological
Arrow of time linked to the thermodynamic arrow.
our subjective experience of time moving forward, remembering the past, anticipating the future, seems closely tied to physical processes that increase entropy. The formation of memories, for instance, involves complex neurological processes that dissipate heat and increase the overall disorder of the brain and its environment. It's plausible that our mental timeline is fundamentally grounded in the physical tendency towards disorder. Our inner clock may be driven by the unwinding spring of the cosmos. Could time run backwards in some other part of the universe or before the Big Bang? Some speculative cosmological models propose scenarios where entropy might decrease in certain regions or epochs. Could there be universes where time effectively runs backwards relative to ours, where broken eggs unscramble and people remember the future? While mathematically intriguing, such ideas face significant theoretical hurdles and lack observational evidence. They remain firmly in the realm of imaginative possibility. Does the cosmic river have hidden countercurrents in unseen places? The fundamental laws of physics mostly work the same forwards or backwards in time. If you watch a video of two billiard balls colliding, the reversed video looks just as physically plausible. Most basic laws governing motion, gravity, and electromagnetism exhibit this time reversal symmetry. This makes the observed arrow of time even more puzzling. If the underlying rules are symmetric, why is the resulting behavior so strongly asymmetric? The rules seem indifferent to direction, yet the game proceeds only one way. The asymmetry seems to come from the universe's overall state, not the basic laws. The prevailing view is that time's arrow is not a property of the fundamental physical laws themselves, but rather a consequence of the specific boundary conditions of our universe, namely, its incredibly low entropy beginning. It's like shuffling a deck of cards. The laws governing the shuffle are reversible, but starting with an ordered deck inevitably leads to a disordered state. The direction emerges not from the rules, but from the initial setup of the cosmic game. What would it feel like if time ran backwards? This is a mind-bending thought experiment. If all physical processes, including our neurological ones, were running in reverse, would we perceive time flowing backwards? Or would our consciousness also run in reverse, meaning we would still feel like we were moving forwards, but towards the past, unremembering things as they happened? it's possible that the subjective experience of forward time flow is intrinsically linked to the direction of increasing entropy, making a reversed perception impossible. Could consciousness flow upstream against the current of entropy? At the smallest scales, time itself might become fuzzy or uncertain. Just as quantum mechanics introduces uncertainty in position and momentum, Heisenberg's uncertainty principle, some theories suggest a similar uncertainty might apply to time and energy. At incredibly short durations near the Planck time, the concept of a precise moment might lose its meaning, dissolving into a probabilistic fuzziness. Time might not be a perfectly sharp coordinate, but might possess an inherent quantum jitter. The ticks of the universe's smallest clock might blur together. Does time flow smoothly, or does it jump in tiny discrete steps? Related to the idea of Planck time is the question of whether time is continuous, like a perfectly smooth river, or quantized, progressing in tiny, indivisible packets. If time is discrete, then reality unfolds like a movie projector, frame by minuscule frame. While most mainstream theories treat time as continuous, some alternative models explore the possibility of a quantized temporal structure, though verifying this experimentally is far beyond current capabilities. Is duration a seamless glide or a sequence of infinitesimal leaps? Quantum tunneling allows particles to seemingly borrow time from the future. This bizarre quantum phenomenon allows a particle to overcome an energy barrier it doesn't classically have enough energy to surmount. One interpretation, related to the time-energy uncertainty principle, suggests the particle can momentarily borrow the needed energy, provided it pays it back within a timescale allowed by the uncertainty principle. It's as if the particle takes a fleeting, unobservable loan from the near future to make an impossible leap in the present. Quantum mechanics permits fleeting overdrafts on the bank of time. Entangled particles seem to influence each other instantly, regardless of distance, challenging notions of time. When two quantum particles are entangled, measuring a property of one particle instantaneously determines the corresponding property of the other, no matter how far apart they are. This spooky action at a distance seems to violate the principle that nothing can travel faster than light, suggesting a connection that operates outside the usual constraints of space-time and potentially challenges our linear concept of cause and effect across time. Entanglement hints at connections deeper than space and potentially independent of time. Does measuring a quantum particle now affect its state in the past? Experiments like the delayed choice quantum eraser produce results that are difficult to interpret without invoking some form of retro-causality. The choice of how to measure a particle after it has completed its journey seems to influence the behavior it exhibited during that journey, e.g., whether it acted like a wave or a particle. While not allowing information to be sent to the past, these experiments blur the intuitive line between present actions and past realities. The present observation seems to reach back and shape the history of the observed. Some interpretations of quantum mechanics suggest multiple timelines or parallel universes. The many worlds interpretation, MWI, proposes that every quantum measurement doesn't cause a collapse into one state, but instead causes the universe to split into multiple branches, one for each possible outcome. In this view, all possibilities are realized in separate parallel timelines. This avoids the measurement problem but implies the existence of an exponentially branching multiverse, where every quantum event creates new, diverging histories. Every quantum coin flip lands on both heads and tails, each in its own distinct reality. Every quantum choice might create a branching reality. If MWI is correct, then every time a quantum system in superposition interacts and decoheres, the universe splits. This happens constantly everywhere, creating an unimaginably vast ensemble of parallel worlds, each representing a different sequence of quantum outcomes. Your own life would exist in countless variations across these diverging timelines, each path representing a different set of choices made at the quantum level. The tree of possibilities grows infinitely dense with every passing moment. The feeling of anticipation shapes our experience of future time. Our ability to project ourselves mentally into the future, to anticipate upcoming events with pleasure or dread, strongly colors our relationship with time. Anticipation can make time seem to drag, waiting for a desired event, or fly, approaching an unwanted deadline. Our orientation towards what is yet to come is a powerful force in our subjective experience of duration. The shadow of tomorrow stretches back to color today. Nostalgia shapes our experience of past time. Similarly, our relationship with the past is not just a neutral record, but is deeply influenced by emotion. Nostalgia, the sentimental longing for a past often perceived through rose-tinted glasses, can make bygone eras feel particularly warm, simple, or significant. Our emotional connection to memories actively shapes how we feel about the time that has elapsed. Memory is not just a record, but a landscape colored by feeling. Boredom can make time feel incredibly slow. When we are disengaged, understimulated, and actively monitoring the passage of time, minutes can feel like hours. This subjective stretching of duration during boredom highlights how much our internal sense of time is linked to our level of engagement and the density of meaningful events occurring within a given interval. Time seems to expand when our minds have little else to occupy them. An empty moment can feel heavier than a full hour. Cosmic time is the standard clock used to measure the age of the universe. Cosmologists use a theoretical concept called cosmic time, which represents the time elapsed since the Big Bang as measured by a hypothetical observer at rest relative to the overall expansion of the universe. This provides a common timescale for describing events throughout cosmic history, allowing us to speak meaningfully about the age of the universe, currently estimated at 13.8 billion years, and the timing of different epochs. It is the master clock synchronized with the expansion of space-time itself. Different celestial objects
Have vastly different timescales.
The universe operates on timescales that dwarf human comprehension. A massive, bright star might burn through its fuel and explode as a supernova in just a few million years. A sun-like star lives for around 10 billion years. A small, cool red dwarf star might continue fusing hydrogen for trillions of years, far longer than the current age of the universe. Cosmic events unfold across an immense spectrum of durations. Nature operates clocks that run from fleeting instants to near eternities. A red dwarf star might live for trillions of years. These small, dim stars are incredibly fuel efficient. They burn their hydrogen fuel so slowly that their expected lifespans are vastly longer than the 13.8 billion years the universe has existed so far. In the far distant future, long after stars like our sun have died,
Red dwarfs will still be quietly shining.
the last bastions of stellar light in an increasingly dark cosmos. They are candles lit for a vigil that will outlast the present age of the universe. The universe itself might endure for unimaginable lengths of time. Depending on its ultimate fate, the universe could continue expanding for trillions upon trillions of years, perhaps even longer. Future epochs might involve the slow decay of matter itself, the gradual evaporation of black holes, and eventually, possibly, a final state of near-perfect emptiness and equilibrium known as heat death. The timescale of the universe's potential future dwarfs even the immense age it has already attained. The cosmic story may continue long after the stars have gone out. The far future might involve the slow evaporation of black holes. According to Hawking radiation theory, black holes are not eternal, but slowly lose mass over immense timescales. In the very distant future, after all stars have died and galaxies have dispersed, the universe might enter a black hole era dominated by these objects. Eventually, even they would evaporate, leaving behind only a diffuse bath of low-energy particles. This process represents one of the longest and slowest clocks imaginable. Even the ultimate prisons of gravity will eventually dissolve back into time, or perhaps the universe will end in a big rip, tearing itself apart. If the mysterious dark energy causing the universe's accelerated expansion continues to strengthen, it could lead to a dramatic end scenario. In a big rip, the expansion would become so rapid that it would eventually overcome the forces holding galaxies, stars, planets, and even atoms together, tearing all structures apart in a final, accelerating disintegration of space-time itself. Time in this scenario might end abruptly. The fabric of reality could unravel at an ever-increasing speed. Time itself might end if the universe recollapses in a big crunch. If the density of the universe is high enough, gravity could eventually overcome the expansion, causing the universe to stop expanding and begin contracting. This could lead to a final big crunch, where all matter and space-time collapses back into a singularity similar to the Big Bang. In such a scenario, time as we understand it would cease to exist at the moment of final collapse. The cosmic clock could run down and then implode upon itself. The cycles of day and night give us our most basic sense of time. The regular rotation of the Earth, creating the alternation of light and darkness, is perhaps the most fundamental external timekeeper for life on our planet. This steady, predictable rhythm has shaped biological clocks, agricultural cycles, and human patterns of activity for millennia. It provides the primary beat against which we measure our lives. The turning of the planet is our primordial metronome. The orbit of the Earth around the Sun defines our year. The longer cycle of the Earth's revolution around the Sun, bringing with it the changing seasons, provides another crucial natural timescale. The year serves as a fundamental unit for measuring longer durations, marking anniversaries, tracking ages, and structuring agricultural and social calendars. Our journey around the Sun provides the larger
rhythm of our temporal experience. The
annual orbit draws the circle within which we mark longer passages. Ancient civilizations built structures to track the passage of time. From Stonehenge aligned with the solstices to the pyramids potentially used for astronomical observations, numerous ancient cultures invested enormous effort in creating monumental calendars. These structures allowed them to predict seasonal changes, regulate agricultural cycles, and mark ceremonial occasions, demonstrating a deep human need to measure and understand the patterns of time. Stone and shadow were the first instruments used to grasp duration. Our modern clocks are based on the
incredibly regular vibrations of atoms.
The most precise timekeeping devices today are atomic clocks. These rely on the fact that atoms, specifically electrons transitioning between energy levels, oscillate or vibrate at extremely stable and predictable frequencies. By locking an electronic oscillator to the frequency of these atomic transitions, often using cesium or rubidium atoms, we can create clocks of astonishing accuracy. We measure time by listening to the resonant hum of matter itself. Atomic clocks are accurate to within 1 second over billions of years. The stability of atomic oscillations allows for timekeeping precision that far surpasses any mechanical or astronomical clock. The current generation of atomic clocks are so accurate they would lose or gain less than a second over the entire age of the universe. This precision is essential for technologies like GPS, internet synchronization, and fundamental physics research. Humanity has learned to track moments with almost perfect fidelity. Standardizing time across the globe was a major challenge. Before the late 19th century, time was largely a local affair, with towns setting their clocks based on the local solar noon. The advent of railways requiring coordinated schedules across distances necessitated the development of standardized time zones. This required international agreements and fundamentally changed how societies related to and measured time. The synchronization of clocks mirrored the shrinking of the world. Time zones are a human invention to manage the rotation of the Earth. They are a practical compromise Dividing the globe into 24 zones, each ideally spanning 15 degrees of longitude, within which clocks are set to the same hour, while reflecting the physical reality of the Earth's rotation, the specific boundaries and rules like daylight saving time are purely human conventions designed for social and economic coordination. We draw lines on the map to partition the continuous flow of sunrise. The international date line marks the boundary between calendar days. Located roughly along the 180th meridian in the Pacific Ocean, this imaginary line is where one calendar day officially ends and the next begins. Crossing it eastward means setting your calendar back a day, while crossing westward means advancing it. It is a necessary convention to reconcile standardized time zones on a spherical planet. It is the seam where yesterday meets tomorrow on the globe's temporal fabric. Leap seconds are occasionally added to keep our clocks aligned with the Earth's slowing rotation. The Earth's rotation is not perfectly constant. It is gradually slowing down due to tidal friction from the Moon. To prevent coordinated universal time, UTC, based on highly stable atomic clocks from drifting too far from time based on the Earth's actual position relative to the Sun, UT1, a leap second is occasionally inserted, usually at the end of June or December. This momentarily pauses atomic time to let the
Earth catch up. Our most
precise clocks must occasionally wait for our slowing. Planet.Zeno's paradox asks how motion is possible if you must always cross half the remaining distance. This ancient Greek paradox, attributed to Zeno of Elea, challenges the concept of motion through infinite divisibility. To reach a destination, an object must first cover half the distance, then half the remaining distance, then half of that remainder, and so on infinitely.
How can an infinite number of steps be completed in a finite time?
The resolution involves understanding limits and infinite series in calculus, showing that an infinite sum can converge to a finite value. Can an infinite sequence of subdivisions constitute a finite journey? Hilbert's paradox of the Grand Hotel explores the nature of infinity using an infinitely large hotel. Imagine a hotel with infinitely many rooms, all of which are occupied. Can it accommodate a new guest? Yes. Ask every guest to move from room n to room n+1, freeing up room 1. Can it accommodate infinitely many new guests? Yes. Ask every guest to move from room n to room 2n, freeing up all the infinitely many odd-numbered rooms. This paradox highlights the counterintuitive properties of infinite sets. Infinity possesses a capacity that defies finite intuition. The Fermi paradox asks, if time travel or fast space travel is possible, where are all the aliens? This paradox extends beyond just time travel. It questions why, given the vastness of the universe and the high probability of other intelligent life, we see no evidence of extraterrestrial civilizations. If interstellar travel or communication is feasible, even at slow speeds over long timescales, shouldn't the galaxy be teeming with detectable activity? The silence is puzzling. The vastness implies neighbors, yet the cosmos seems empty. Perhaps advanced civilizations discover time travel is too dangerous or impossible. One potential resolution to the temporal aspect of the Fermi paradox is that backward time travel simply cannot be achieved, or that any civilization capable of it understands the risks of paradoxes and strictly avoids interfering with the past. Alternatively, perhaps the physical requirements are so extreme that it remains forever out of reach. Even for highly advanced societies, mastery of time might come with ultimate restraint, or remain an unattainable dream. The Boltzmann brain paradox suggests your current conscious state might be a random fluctuation. In a universe that exists for an extremely long time and tends towards disorder, it's statistically possible for random fluctuations to momentarily create ordered structures. The paradox arises because it might be statistically more likely for a single, conscious brain with all its memories and sensations to randomly fluctuate into existence out of chaos than for an entire ordered universe like ours to arise. This challenges our assumption that our perceptions reflect a genuine, ordered past. Is the perceived order of history more improbable than the spontaneous emergence of a single, dreaming mind? The twin paradox explores the consequences of time dilation in relativity. Consider identical twins. One stays on Earth while the other takes a round-trip journey on a spaceship traveling near the speed of light. Due to velocity-based time dilation, the traveling twin experiences less time passing. Upon returning, the traveler finds they are younger than the twin who remained on Earth. This striking prediction of special relativity has been experimentally
Verified using atomic clocks on airplanes and
satellites. A journey at high speed alters the traveler's personal measure of elapsed time. But from the traveling twin's perspective, wasn't the Earth twin moving away? The apparent paradox arises when considering the situation from the traveler's frame of reference. Relative to the spaceship, the Earth zooms away and then returns. Why doesn't the Earthbound twin age less? The resolution lies in the asymmetry of the situation. The traveling twin must accelerate to leave, turn around, and decelerate to return. This acceleration breaks the symmetry and makes the traveler's frame non-inertial, validating the Earthbound twin's perspective as the one experiencing more time acceleration. Is the key that unlocks the asymmetry in relative aging. The ticking clock argument against time travel suggests altering the past is impossible. This philosophical argument posits that the very notion of changing the past is incoherent. If an event occurred in a certain way, that is how it occurred. Traveling back to that moment doesn't erase the original event. It simply means you were also present when it happened the first time. The past, in this view, is a fixed record, and any perceived changes are merely revelations of details that were always part of that record. The ink of history, once dry, cannot be erased, only perhaps reread. What if time resists changes, like a river flowing around a stone? The Novikov's self-consistency principle offers a more physical perspective. It proposes that the laws of physics are configured in such a way as to prevent causal paradoxes. If you traveled back in time with the intent to perform a paradoxical action, the initial conditions would somehow conspire to ensure that you fail. The probability of events that lead to paradoxes would effectively become zero. The universe might possess a fundamental tendency to maintain its own causal integrity.
action taken by a time traveler was already part of history.
According to the self-consistency principle, a time traveler cannot change the past because their journey and actions were already factored into the timeline they experienced before departing. Their presence in the past isn't an alteration, but simply a fulfillment of events that were always going to happen. You don't change history. You become part of it. The loop of time ensures its own unbroken continuity. Is time travel into the future simply a matter of waiting? In the most basic sense, we are all constantly traveling into the future at a rate of 1 second per second. However, relativity offers ways to speed up this journey relative to others. By traveling at relativistic speeds or spending time in a strong gravitational field, one can effectively leap forward in external time while experiencing less personal time. Hibernation or suspended animation could be seen as a form of future time travel. While not involving relativistic effects, placing oneself in a state of significantly reduced metabolic activity for an extended period would allow one to effectively skip forward in time. Years or centuries could pass in the outside world, while the hibernating individual experiences only a brief, subjective duration, awakening in a distant future. Slowing one's internal clock achieves a similar result to accelerating the external world. Our perception of time is linked to our rate of processing information. Subjective time seems related to how much information our brain is processing per unit of objective time. When we are taking in and processing a lot of novel information, like in childhood or during a crisis, time feels slower. When processing is minimal or automatic during routine activities or boredom, time feels faster. Our internal metronome speed seems tied to cognitive load. The richness of experience appears to dilate the perceived moment. flies seem to perceive time more slowly than humans, allowing them to react faster. Smaller animals with faster metabolic rates often process sensory information more quickly than larger animals. A fly might perceive the world at a higher frame rate, making our movements appear slow motion to them, which explains why they are so difficult to swat. Different species seem to inhabit different subjective temporal realities, tuned to their ecological needs. The pace of awareness varies across the spectrum of life. The cycles of day and night give us our most basic sense of time. The Earth's steady rotation on its axis provides a fundamental, external rhythm that has profoundly shaped life on our planet. The regular alternation between light and darkness creates a natural unit of duration, the day, which governs our patterns of sleep, activity, and biological function. This constant planetary pulse is perhaps the most primal and universal clock known to humankind, the first metronome against which we learn to measure our existence. It is the steady, quiet drumbeat of our world. The orbit of the Earth around the Sun defines our year. The longer, slower cycle of our planet's journey around its star gives us another crucial unit of time, the year. This annual passage brings with it the changing seasons, influencing weather, agriculture, and the behavior of plants and animals. The year provides a larger framework for organizing our lives, marking significant events, tracking ages, and structuring societies. Our orbit draws the grand circle within which we chart the longer passages of our lives and histories. Ancient civilizations built structures to track the passage of time. Recognizing the importance of celestial cycles, many ancient cultures invested immense effort in creating monumental astronomical observatories and calendars. Structures like Stonehenge in England, aligned with the solstices, or the El Castillo Pyramid at Chichen Itza, designed to track the equinoxes with shadows, demonstrate a deep-seated human need to connect with,
Measure and predict the rhythms of time.
These silent stone sentinels stand as testaments to our ancestors' patient observation of the heavens. Our modern clocks are based on the incredibly regular vibrations of atoms. While early clocks relied on pendulums or springs, the pinnacle of timekeeping precision today comes from atomic clocks. These devices utilize the fact that electrons within atoms, when transitioning between specific energy levels, absorb or emit electromagnetic radiation at an extremely stable and predictable frequency. By locking an electronic oscillator to this atomic resonance, often using cesium or rubidium, we create clocks far more accurate than any based on macroscopic mechanical or astronomical motion. We measure moments by listening to the universe's most stable hum. Atomic clocks are accurate to within 1 second over billions of years. The phenomenal stability of atomic transitions allows for timekeeping of almost unimaginable precision. The best current atomic clocks are so accurate that they would not gain or lose a single second over a period longer than the current age of the universe. This incredible accuracy is not just a scientific curiosity. It is essential for modern technologies like satellite navigation, high-speed communication networks, and fundamental scientific experiments testing the nature of time itself. Humanity has achieved near perfection in marking duration. Standardizing time across the globe was a major challenge. Before the late 19th century, time was primarily a local phenomenon, with each town setting its clocks based on the apparent position of the sun, local solar time. The advent of railroads and telegraphs, which required precise scheduling across vast distances, created a need for coordinated, standardized time. This led to contentious debates and ultimately international agreements establishing the system of time zones and universal time we use today, fundamentally altering society's relationship with the clock. Synchronizing the world required reshaping our perception of the hour. Time zones are a human invention to manage the rotation of the Earth. As a practical solution to the problem of coordinating time across a rotating globe, the world was divided into 24 standard time zones. Ideally, each zone represents an hour's difference and covers 15 degrees of longitude. However, the actual boundaries are often adjusted for political and geographical convenience. Time zones, along with conventions like daylight saving time, are entirely human constructs imposed upon the continuous reality of the Earth's turning relative to the Sun. We draw lines on the map to create manageable segments of the day's progression. The international dateline marks the boundary between calendar days. Situated roughly along the 180th meridian in the Pacific Ocean, this imaginary line serves as the transition point where one calendar day ends and the next begins. Traveling east across the line means setting your calendar back by a day, while traveling west means moving it forward. It's a necessary human convention to reconcile the global system of time zones and prevent temporal paradoxes as one travels around the Earth. It is the arbitrary seam where today becomes yesterday, or tomorrow becomes today. Leap seconds are occasionally added to keep our clocks aligned with the Earth's slowing rotation. The Earth's spin is not perfectly constant. Tidal forces, primarily from the Moon, cause its rotation to gradually slow down over long timescales. Highly accurate atomic time, UTC, would therefore slowly drift out of sync with time based on the Earth's rotation, UT1, related to solar noon. To keep the difference below 0.9 seconds, an extra leap second is occasionally inserted into UTC, usually at the end of June or December. Our most precise clocks must sometimes pause for a moment to let our planet catch up. Atomic precision yields momentarily to planetary slowdown, Zeno's. Paradox asks how motion is possible if you must always cross half the remaining distance. This ancient philosophical puzzle, one of several attributed to Zeno of Elea, challenges the very concept of traversing a finite distance. To get from point A to point B, one must first cover half the distance, then half of the remaining distance, then half of that remainder, and so on ad infinitum. Since there are infinitely many such halfway points to cross, how can the journey ever be completed in a finite amount of time? The paradox highlights the counterintuitive nature of infinity and continuity. Can an infinite series of steps constitute a finite journey, or does an arrow ever truly reach its target if it must pass through infinite halfway points? Zeno's dichotomy paradox, similar to the Achilles and the tortoise paradox, questions motion by dividing the path into an infinite number of segments. While seemingly logical, the paradox dissolves with the mathematical understanding of convergent infinite series developed through calculus. An infinite sum of progressively smaller terms can indeed add up to a finite total, allowing the arrow to reach its target in a finite time. Despite traversing infinitely many conceptual subdivisions of its path, mathematics shows that infinite subdivisions do not necessitate infinite duration. Hilbert's paradox of the Grand Hotel explores the nature of infinity using an infinitely large hotel. David Hilbert proposed a thought experiment involving a hotel with infinitely many rooms, all of which are currently occupied. If a new guest arrives, can they be accommodated? Yes. Simply ask the guest in room 1 to move to room 2, the guest in room 2 to move to room 3, and so on for all infinitely many guests. Guest n moves to n+1. This frees up room 1 for the newcomer. The paradox illustrates that infinite sets behave differently from finite sets. Adding one element to an infinite set does not change its size, cardinality. An infinite capacity can always absorb one more. Can an infinitely full hotel accommodate infinitely many new guests? Mathematically, yes. The Grand Hotel paradox extends further. If an infinite number of new guests arrive, say on an infinitely long bus, they can also be accommodated. Ask the current guest in room n to move to room 2n. This fills all the even-numbered rooms, leaving all the infinitely many odd-numbered rooms vacant for the new arrivals. This demonstrates the truly bizarre and counterintuitive arithmetic of infinity. Infinity contains infinite room for more infinity. The Fermi paradox asks, if time travel or fast space travel is possible, where are all the aliens? Originally formulated regarding interstellar travel, the paradox questions the lack of observable evidence for extraterrestrial civilizations. Given the high probability estimates for their existence based on the universe's vastness and age, if civilizations commonly arise and develop advanced technologies like interstellar travel or, hypothetically, time travel, why haven't we detected their signals, probes, or visits? The great silence is perplexing. The cosmic stage seems vast, yet the actors remain unseen. Perhaps advanced civilizations discover time travel is too dangerous or impossible. Applying the Fermi paradox to time travel, one possible resolution is that backward time travel is either physically forbidden by unknown laws, technologically unattainable even for advanced societies, or consciously avoided due to the potentially catastrophic risks of altering history or creating paradoxes. The absence of visitors from the future might simply indicate that such journeys cannot or should not happen. Temporal tourism might be fundamentally prohibited or wisely self-regulated. The Boltzmann brain paradox suggests your current conscious state
might be a random fluctuation.
This unsettling thought experiment arises from considering entropy and statistics over immense timescales. In a universe tending towards thermal equilibrium, maximum entropy, random quantum fluctuations could very rarely assemble complex structures. The paradox posits that it might be statistically far more probable for a single, isolated conscious brain, complete with false memories of a past and an external world, to spontaneously fluctuate into existence than for an entire low-entropy universe like ours to arise and evolve. Complexity is the perceived reality of vast cosmic fluke, or could awareness itself be the fluke? This paradox questions our assumptions about entropy and the past. If Boltzmann brains are more probable than our observed universe, why do we find ourselves in such a complex, ordered cosmos with a consistent history? It challenges the idea that our current state is necessarily the result of evolving from an even lower entropy past, the Big Bang. Perhaps our understanding of entropy, probability, or the nature of
Observation itself is incomplete. Our existence
within an ordered history might require explanation beyond simple statistics. The twin paradox explores the consequences of time dilation in relativity. Consider identical twins. One embarks on a high-speed interstellar journey and returns to Earth, while the other remains home. According to special relativity, the traveling twin, having experienced significant velocity-based time dilation, will have aged less than the earthbound twin upon reunion. This difference in aging is a direct consequence of the relativity of time. Speed alters the personal passage of years. The resolution lies in the asymmetry of acceleration. The apparent paradox, why doesn't the Earth twin age less from the traveler's perspective, is resolved by noting that the traveler's journey is not symmetrical. The spaceship twin must accelerate away from Earth, decelerate to turn around, accelerate back towards Earth, and finally decelerate to land. These periods of acceleration distinguish the traveler's frame of reference from the Earth twin's, mostly, inertial frame, breaking the symmetry and confirming the traveler experiences less elapsed time. Changing speed is what distinguishes the traveler's temporal experience. What if time resists changes, like a river flowing around a stone? The Novikov self-consistency principle offers a physical perspective on time travel paradoxes. It postulates that the laws of physics are such that any event occurring in a region of space-time containing closed time-like curves must be self-consistent. In essence, if time travel to the past were possible, you could only perform actions that were already part of history and led to the future you came from. Events would conspire to prevent paradoxes. The timeline might possess a fundamental self-healing property. Any action taken by a time traveler was already part of history. According to Novikov's principle, if you travel to the past, you cannot, for example, prevent your own birth because your existence proves that you were born. Any actions you take were simply the way events unfolded. You might discover you were unknowingly involved in past events, fulfilling a role rather than changing anything. Free will within a causal loop becomes highly constrained or illusory. The journey back simply reveals the threads you always occupied in the tapestry. Is time travel into the future simply a matter of waiting? In the most trivial sense, yes, we all travel into the future at a constant rate. However, relativity provides mechanisms to accelerate this journey relative to a stationary observer. By exploiting time dilation through high speeds or strong gravity, one could experience a short duration personally, while many years pass in the external world. Effectively, leaping forward in time, the future arrives for all. But relativity offers express lanes. Hibernation or suspended animation could be seen as a form of future time travel. While not manipulating space-time itself, significantly slowing down biological processes would allow an individual to traverse a long period of external time while experiencing very little subjective time. Awakening after centuries of suspended animation would be functionally equivalent to arriving in a distant future, having skipped the intervening years. Slowing life's clock allows one to awaken in a later age. Our perception of time is linked to our rate of processing information. Subjective time seems to expand when our brains are rapidly processing novel or complex information, and contract when processing is minimal or automatic. This suggests our internal sense of duration is not a direct reading of an external clock, but is related to the amount of cognitive activity occurring within a given interval. More mental work seems to equal a longer subjective moment. The perceived length of a moment scales with the density of its contents. Flies seem to perceive time more slowly than humans, allowing them to react faster. Smaller animals often have faster metabolic rates and neural processing speeds. A fly might process visual information at a much higher frame rate than a human. This means that from the fly's perspective, our movements appear to be happening in slow motion, giving them ample time to react and evade a swat. Different species seem to inhabit distinct temporal realities, optimized for their survival needs. Life unfolds at different subjective speeds for different creatures. Does time exist independently of observers? This is a deep philosophical and physical question. If the universe contained no matter, no energy, and crucially, no change, would time still pass? Some argue that time is fundamentally relational. It is a measure of change. Without change, the concept of time becomes meaningless. Others argue that space-time is a fundamental backdrop that exists whether or not anything is happening within it. Is time the stage, or is it merely the progression of the play? If the universe were completely empty and static, would time still pass? In a hypothetical universe devoid of all particles and fields, undergoing no expansion or contraction, it's difficult to define what the passage of time would even mean. Without events to sequence or processes to measure duration, time loses its operational definition. This thought experiment highlights the deep connection between time and physical change. Duration requires events to measure its passage. Some theories suggest space might be emergent, arising from a deeper reality. Could time be too? Cutting-edge physics research explores ideas where space-time itself is not fundamental, but emerges from underlying quantum information or network structures. Just as temperature emerges from particle motion, space and time might be collective properties of a more basic layer of reality. In such theories, the familiar flow of time could be an approximation valid only at macroscopic scales. The dimensions we inhabit might be
woven from something more fundamental.
Would a being that perceives all of time at once experience? Speculative fiction often explores the idea of beings who exist outside of linear time, perceiving all moments, past, present, and future, simultaneously. From such a four-dimensional perspective, history would not unfold but would exist as a static landscape. Concepts like causality, free will, and the passage of time itself might be entirely different or meaningless. Seeing the entire river at once transforms the meaning of flow. Our language often uses spatial metaphors for time. We talk about looking forward to the future, events being behind us, a long time, or approaching a deadline. This pervasive use of spatial terms to describe temporal concepts suggests a deep cognitive link between how we conceptualize space and time. Perhaps our minds inherently understand duration by analogy with distance. We navigate time using maps borrowed from space. Does this reflect a deep connection between space and time in our minds? The intimate connection between space and time, revealed by relativity, might be mirrored in the way our brains process and represent these concepts. Our neural architecture for spatial navigation and temporal sequencing might share common roots, leading to the natural use of spatial language when discussing time's abstract nature. Our mental models seem to echo the physical unity of space-time. The ticking of a clock is a human invention to measure something intangible. Time itself cannot be directly seen or touched. Clocks are merely devices we have created that undergo regular, periodic motion, which we then use as a proxy to quantify the abstract concept of duration. The steady ticking is a human-imposed rhythm, an attempt to give concrete measure to the elusive flow of moments. We grasp the intangible by counting the oscillations of the tangible. Is the passage of time purely subjective, a feature of consciousness? Some philosophical viewpoints argue that the feeling of time passing, the dynamic sense of becoming, is entirely a product of conscious awareness. In this view, the physical universe might simply exist as a static block of space-time, eternalism, and the flow is generated internally by our minds as we experience different slices of this block sequentially. Could the river's current be an artifact of the observer's journey along its bank, or is it an objective feature of the physical world? Alternatively, the passage of time might be a real, physical process occurring independently of observers. Perhaps there is a genuine, objective unfolding of moments, or perhaps the asymmetry related to entropy represents a fundamental directionality inherent in the cosmos itself. The debate between subjective and objective time remains unresolved. Does the universe itself possess a present moment that advances? The concept of wasting time implies time is a finite resource. Our cultural anxiety about productivity and efficiency often leads us to view time as something limited that must be used wisely. This perspective treats time like a currency or commodity. While our individual lifespans are finite, whether time itself is finite or infinite remains an open cosmological question. Our mortality lends urgency to the moments we possess. Our mortality gives time its precious quality. The knowledge that our individual existence is finite imbues each moment with significance. If time were infinite and reversible, choices might lose their weight, and experiences might lose their unique value. The unidirectional flow of time and the finitude of life contribute profoundly to the meaning and poignancy of human experience. The awareness of ending bestows value upon the interval. Every moment is unique and will never come again. Assuming the past cannot be revisited or changed, each instant is singular. The specific configuration of the universe, the content of our thoughts, the surrounding events, all combine to create a unique moment that occurs once and then recedes into the past, accessible only through memory. This uniqueness underscores the irretrievable nature of elapsed time. The river carries each drop of water past only once. The past exists only in memory and physical records. Once a moment has passed, its direct existence ceases. It persists only indirectly, either as neurological patterns in brains, memories, or as physical traces in the environment, fossils, documents, geological strata, light from distant stars. Reconstructing the past always involves interpreting these remnants left behind in the present. History resides in the echoes and archives it leaves behind. The future exists only as possibility and prediction. Unlike the past, the future has not yet left any physical trace. It exists only as a range of potential outcomes shaped by current conditions and the laws of physics, and as mental projections based on anticipation, planning, and probability. The future is the realm of the potential, not the actual. Tomorrow is a landscape of probabilities yet to solidify. Only the present moment is directly experienced. Despite the difficulties in precisely defining now, it remains the locus of our direct conscious experience. We live, perceive, and act within the present. The past is accessed through memory, the future through anticipation. But only the present possesses the quality of immediate reality. Awareness resides perpetually at the cusp of becoming. Yet, the definition of the present remains elusive. Philosophically, psychologically, and physically, pinning down the precise nature and duration of the present moment is remarkably difficult. Is it an infinitesimal point? A brief window? A purely subjective construct? Its seemingly simple nature dissolves into complexity upon closer examination. The now is both intimately familiar and profoundly mysterious. Time is perhaps the greatest and most intimate mystery. It is the fundamental dimension within which our entire lives unfold. We are immersed in it, yet we struggle to define it or fully comprehend its properties. Its apparent simplicity masks deep paradoxes and connections to the most fundamental aspects of reality, from quantum mechanics to cosmology. It governs everything, yet remains profoundly difficult to grasp. Time dictates sequence, causality, and change. It sets the rhythm for all physical processes and biological life. Yet, its essential nature, whether it flows, whether it's fundamental or emergent,
its ultimate origin and fate remains.
One of the most challenging and persistent questions in science and philosophy, the master regulator of
existence resists easy definition. The
paradoxes of time invite us to question our deepest assumptions about reality. Engaging with concepts like time dilation, the relativity of simultaneity, causal loops, and the arrow of time forces us to confront the limitations of our everyday intuition. These paradoxes serve as valuable tools, pushing us towards a more nuanced and accurate understanding of the strange, beautiful, and deeply interconnected nature of the universe. Contradictions serve as signposts, pointing towards deeper truths. Our subjective experience of time's flow might be linked to consciousness itself. Some theories propose that the feeling of time passing is not just a perception of physical processes like entropy, but is intrinsically related to the nature of conscious awareness. Perhaps consciousness is a process that inherently unfolds sequentially, creating the subjective arrow of time, even if the underlying physical reality is timeless. Could the feeling of passage be the defining characteristic of awareness? The block universe view offers a potentially timeless perspective. If eternalism is correct and all moments exist simultaneously, then reality can be viewed as a static, four-dimensional block of space-time containing the entire history of the universe. From this perspective, change is an illusion perceived by observers tracing paths through the block, but the block itself is unchanging and eternal. The entire cosmic drama might exist as a single, complete sculpture. Thinking about time paradoxes can be a form of mental stretching. Grappling with these logical puzzles, even if they remain unresolved, exercises our capacity for abstract thought and challenges our ingrained assumptions. It encourages flexibility of mind and an appreciation for the subtle and often counterintuitive nature of reality as described by modern physics. Wrestling with temporal knots can strengthen our cognitive grasp. The mystery of time connects physics, philosophy, neuroscience, and psychology. Understanding time requires insights from multiple disciplines. Physics describes its behavior in relation to space, gravity, and quantum mechanics. Philosophy explores its fundamental nature and logical structure. Neuroscience investigates how the brain constructs our perception of it. Psychology studies our subjective experience of its passage. A complete picture requires weaving these different threads together. Time sits at the intersection of many paths of human inquiry. Perhaps our linear perception of time is an evolutionary adaptation. For creatures like us who operate based on cause and effect, Remembering the past to predict and navigate the future is essential for survival. Our strongly linear sense of time might be a cognitive tool shaped by evolution, allowing us to function effectively in a world governed by entropic processes, even if it doesn't reflect the ultimate. Underlying nature of time itself, our temporal sense might be a survival tool, not a perfect mirror of reality. Ultimately, the true nature of time remains one of science's most profound and alluring open questions. Despite centuries of contemplation and investigation, time continues to hold deep mysteries. Its relationship with quantum gravity, the origin of its arrow, its potential beginning and end, these are frontiers where our current knowledge gives way to speculation and wonder. The quest to understand time is a journey that continues. The river of time still guards its deepest secrets. And so, our gentle drift through the currents and paradoxes of time draws to its peaceful conclusion. We have wandered through the strange elasticity of relativity, pondered the unwavering direction of time's arrow, and considered the very fabric of the moments we inhabit. The echoes of these perplexing and wondrous ideas can now begin to settle, like ripples fading on a quiet pond, leaving only a sense of calm stillness behind. It is time to let it all go. We have explored the notion that time might stretch and shrink, that the past might coexist with the present, and that our own perception of its flow is a complex creation of our minds. We have touched upon the profound mysteries linking time to the universe's beginning, its tendency towards disorder, and the strange rules of the quantum realm. Let the feeling of this deep and intricate
mystery be a source of quiet comfort, the same elusive time that
governs the expansion of the cosmos and the ticking of atomic clocks also governs the gentle rhythm of your own breath, the steady beat of your heart. You exist within this temporal flow, a conscious awareness experiencing this unique present moment. You are a part of this grand and perplexing temporal tapestry. And now, as you allow yourself to drift further down into the welcoming depths of sleep, release all thoughts of paradox and duration. Let your mind become as peaceful and still as a theoretical point outside of time altogether. There are no more questions to answer, no more concepts to grasp. Your only task now is to rest, to surrender to the quiet, to allow the gentle current of sleep to carry you into a state of timeless peace. May your rest be deep and restorative. Good night.